Hello, my name is Rachel Harvey, and today, along with my teammates, we'll be presenting our mission concept for Mission to Titan. We'll begin our presentation with establishing the need for our mission. Titan is Saturn's largest moon and is the only natural satellite in our solar system with a significant atmosphere. There are known methane and ethane liquid bodies on Titan, as well as subsurface water. This presence of water may indicate a possibility of life and will provide vital insight on Earth's geological and chemical evolution. Previous NASA missions have only landed on Titan's surface for approximately 90 minutes, which was not enough time to provide significant scientific data for scientists and NASA experts. The stakeholders for this mission are NASA as well as the global scientific community, including geologists, chemists, and those studying the origins of life in our universe. The needs of our stakeholders are to develop this mission within 15 years. The mission should have a vehicle operating in Titan's environment, surveying the moon's surface and atmosphere, as well as sending images, videos, and data back to Earth. The mission should investigate a minimum of 5 different locations on Titan's surface and should be able to operate autonomously. Our mission to Titan will employ a rotorcraft air vehicle to swiftly move between locations on Titan's surface. Current state of the art for off-Earth air vehicles is exemplified with the Mars helicopter Ingenuity. Ingenuity was the first to achieve powered flight off Earth and was a miniaturized design intended for the Mars Perseverance rover. Ingenuity is a great starting point for our rotorcraft concept. However, our design is a much larger vehicle than Ingenuity is. The current structures for rotorcraft is primarily composites, as well as aluminum alloys for vehicles that need to be more durable. Drones and small air vehicles use helicopter, tricopter, quadcopter, and even octocopter configurations, depending on their requirements. Our primary competitors are NASA's Jet Propulsion Laboratory, Johns Hopkins Applied Physics Lab, European Space Agency, Lockheed Martin, and Deep Space Industries. Pictured to the right is Johns Hopkins Applied Physics Laboratory's Dragonfly vehicle concept. And now we have our concept of operations for our mission to Titan. We'll begin with our launch vehicle departing Earth and traveling to Titan. Our launch vehicle will arrive in Titan's orbit, and then the heat shield will deploy and separate from the launch vehicle. The heat shield is intended to protect our Titan rotorcraft until it is safely in Titan's atmosphere. Once the heat shield has entered Titan's atmosphere, the tricopter will deploy. And as the tricopter descends through Titan's atmosphere, its sensors and meteorological suite will begin collecting significant data, as well as taking photos and videos. After the tricopter has descended, it will autonomously navigate to a safe location on Titan's surface. The tricopter will then begin drilling and collecting seismic samples from the desired location. Once data, images, and videos have been collected sufficiently, this information will be relayed back from the tricopter to an Earth-based relay station, as well as any prominent mission information will be relayed back to our tricopter on Titan.
Hey everyone, I am Ananya Kapoor and I will be defining the problem for our project. In order to make our mission a success, we have identified certain goals and objectives. The primary objective is to operate the rover efficiently at Titan's atmosphere, which has a low temperature and a high pressure. We aim to maximize our rover's range, the flying altitude, as well as the power efficiency. The science objectives include to look for life on Titan by searching for biomarkers. For this, the mission includes a soft landing of rover on the Titan surface, flying to the specific location, collecting the samples, analyzing them, and sending the generated data back to the Earth. As it is a highly critical mission, it has various constraints. The main constraint is the nominal functioning of the rover at the given temperature and pressure. We need the collected samples from the wide-ranging environments to be free from any physical or chemical perturbations. As it is a high-cost project, getting constant funding might be a constraint. Due to the huge distance between the Earth and Titan, sending back the generated data is also going to be a huge challenge. In order to develop our mission properly, we have created a functional architecture depicting all the main functions of our system. Our rover must reach the Titan surface safely, fly to the specific locations, collect the sample, store them, transfer them to the science instruments, analyze, as well as send the generated data back to the Earth for processing, so that it can be given to the stakeholders, the general public, and the scientific community, and finally archived for future reference. We have made a functional flow block diagram in order to illustrate the sequence of operations of our mission. It has been broken down into 4 levels. The top level tells a broad overview of the flight mission, with the subsequent levels elaborating on the mission operations, acquisition of data, and the collection of samples. In order to fulfill the goals of our mission and satisfy customer needs, a QFT has been prepared. It maps the relations between the customer needs and the engineering characteristics, gives insight about our competing products, helps to assess the most important engineering characteristics, and establish target values. The engineering characteristics have been finalized, keeping in mind the factors that are important for the success of the mission, as well as to proficiently meet our stakeholder needs. Some important functional requirements include power, operating environment, mass, data storage, range, altitude of flying, sample collection, analysis, etc. Here is a summary of our final customer and functional requirements that are used in our QFT. The relationship matrix shows the relationship between the customer and the functional requirements. We infer that power has a strong relation with most customer requirements. Also, all the science requirements have a strong relationship with sample collection and analysis. Although mass does not have many strong relations, it is necessary to minimize it in order to improve the overall efficiency of the rover. A correlation matrix tells us the correlation between different functional requirements. We notice that the power operation has a positive correlation with almost all of the other functions. As the mass of the rover negatively impacts its performance, like the range and the altitude of flying, it has few negative correlations. Here, the direction of improvement for the engineering characteristics is also shown. An importance rating from 1 to 5 has been assigned to the customer requirements, with 5 being the most important. Successful operation in the Titan's atmosphere is considered the most important factor, with the other important requirements being the communications and surveying. The absolute importance is calculated from the relationships identified in the room number 3. And the relative rate importance is calculated from the values that are obtained from the absolute importance. It is observed that the power is the most important functional requirement for the success of the mission. To meet the science goals, the sample collection and analysis is found to have a huge impact. A competitive assessment study was performed in order to assess our standards with other companies' existing products. NASA is also building a similar rover to explore Titan. However, our rover's capability to fly to different locations, collect the samples from different environments, our refueling technology, and most importantly, a set time for the development, as well as the low cost of development, gives us an edge over their product. Furthermore, a technical competitive assessment is also performed, and we conclude that our technology is at par with the NASA's current developing product. It is better than the other products produced by ESA, Lockheed Martin, etc. Hence, our product should be preferred over the other products because of its set development timeline as well as the low cost. Finally, technical difficulty levels and target values have been established, and it is found that reducing the mass of the rover, flying to high altitudes, and transcending the data back to the Earth at high speed would pose a huge challenge in order to make this mission successful. Now, I would like to hand over to Yohannes for going through the establishment of values section.
Hello, my name is Yohannes Kasseya, and I'll be going over the system requirement formulation and modeling of said requirements and overall system. So the first part of the process is to develop the functional requirements for the vehicle system, and the subsystem and subcomponents. As listed in the table here, we have the vehicle at the top level and its respective subcomponents accompanied by the description. So for example, we have mission cost, mass, data handling, and power as the top requirements. From the requirements outlined in the previous slide, the requirements diagram seen here was created using SysML software Magic Draw. As can be seen in the figure, we have the vehicle at the top level and the different subsystem decompositions. So here I'll dive a little deeper into the different system decomposition and their respective requirements. So on the left side, we have cost, which is driven by our budget constraint of $850 million. And on the right side, we have the mass requirement of 300 kilograms, which is driven by our budget constraint in an attempt to reduce overall cost. And the mass requirement is decomposed further into the three listed here, which are science instrument, bus, and structural mass. Next is the data handling and processing, which covers the collection, processing, storage, and transmission of data collected during operations. These requirements are driven by technological limitation, ConOps, as well as design. So things are further composed into different that I named. Next, we have the nominal operation requirements. The vehicle is going to be operating in a hostile environment, and as such, it has to withstand such conditions to operate nominally. So here we have the pressure and temperature conditions outlined that they have to withstand to operate nominally. Next, we have the power subsystem, which covers the generation and storage of power necessary for nominal operation, as well as contingent cases. So for the generation portion, we have solar power and RTG, and for storage, we have batteries. Lastly, we have conditions such as mission duration, frequency, and so the following part of the processing is modeling the system in Magic Draw. As seen in the figure to the left, we have, again, the vehicle at the top level, and it's decomposed into subsystems and subcomponents as seen in the figure. The different subsystems are power, propulsion, science payload, and communication. Diving a little deeper into the different subsystems again, we have the power subsystem here, which outputs mass, cost to the overall model, and has the value parameters such as battery percentage, full battery capacity, and recharge rate. Next, we have the propulsion subsystem, which again outputs mass, cost, and power consumption for the simulation portion of this modeling, and it has the value parameters listed here. Next, we have the science payload subsystem, which again outputs mass, cost, and power consumption. And the science payload is further decomposed into its subcomponents as seen in the diagram at the bottom. Lastly, we have the communication subsystem, which again outputs mass, cost, and power consumption, which will be used in the simulation to evaluate our. For the simulation portion of this model, we have the power subsystem constraint modeling depicted here. Here, the overall power conditions, such as power capacity and current battery percentages, are being calculated. The vehicle will be used, or this will be used to determine the power conditions and validate the power requirements discussed earlier. Next, we have the overall system constraint model, which is trying to calculate the overall cost and mass of the system using the different parameters from the different subsystems. Using this model, test cases can be simulated to assess whether requirements discussed earlier have been met.
I'm Matt Marcus, and I will be going over a trade study my group performed on data collection methods, verification of different systems and subsystems for our vehicle, and the risk associated with some aspects of our mission. One of the most important aspects of our mission is data collection. For this reason, instead of going with the obvious camera imaging, we wanted to make sure we highlighted many possible data collection methods. The mission will truly succeed and fulfill requirements with the use of multiple methods from this list. Alternatives we compared include simple camera imaging, video, physical samples, vehicle system information, and ground vibration transducer data. Camera and video imaging, as well as physical sampling on Titan, will allow for a better understanding of the composition of the moon and its environment. Vehicle systems information gives crucial info on what works best and how to improve for future missions. Ground transducers allow for surveying of the surface itself to get a rough makeup and determine if drilling would harm the stability of the ground. This decision matrix weighs these alternatives against criteria such as reliability, electrical storage space required, weight, size, range, and cost. We can see that camera imaging and vehicle systems are some of the most reliable and easiest to incorporate into our mission. This doesn't necessarily mean they're the most preferred, though, because of our requirements. This shows how each alternative would integrate into our vehicle, but not their importance to the mission. One of our main goals, for instance, is to use physical sampling to test Titan's surface. This is why we added a second step to the matrix, which incorporates weights to show the importance of each to the mission. We weighed physical samples as the most important, next being camera imaging and vehicle systems, and following that, video and ground seismic info. With these new values, the weighted total much more closely resembles the major aspects of the mission, even if some, such as physical sampling, are much more difficult to include. For verification, we created a verification table for our requirements along with the success criteria and the method of verification. These requirements should look familiar, so let's focus on the most important ones, the requirements that used testing for verification. The squared and red requirements are ones that are verified by testing. As we zoom into these 5, we can split them up further into verification of sampling and verification of overarching vehicle criteria. For sampling, our requirements include that the vehicle will collect samples on Titan's surface and that the vehicle will conserve these samples until testing is complete. Testing of item 4 requirement includes a custom habitat mimicking Titan to test drilling and scooping subsystems. Testing for item 5 includes the vehicle's conservation chamber for the max amount of time allowed by our requirements to test the samples if they have been contaminated or not properly conserved. For our vehicle, we have 3 requirements that require testing. 2 of these, items 6 and 7, both apply to the flight of the vehicle and may be tested together to streamline the process. These are that the vehicle flies up to 50 kilometers in altitude and that the vehicle is able to fly at least 45 minutes per mission. These shall be tested under conditions of that similar to Titan in order to not make any incorrect assumptions. Our last test requirement is that the vehicle must be able to operate on Titan's surface. The surface pressure and temperature are much different from Earth, and so must be tested to ensure our vehicle will operate properly. Lastly, let's move on to the risks involved in our mission. These risks range from complete failure of the vehicle, such as item 1, to subsystems inhibited by mission issues, like number 3. A better way to look at these risks is to separate them into categories of low, medium, and high-risk failures. Once separated, we can see that we have 4 items of low risk, 4 of medium risk, and 1 high-risk concern. The risk matrix to the right determines these risks, accounting for their probability as well as their impact. As an example, low risk number 1, a material failure due to the temperature and climate of Titan, is shown by L1 at the top left of the graph. Although M4 is a catastrophic failure due to vehicle destruction during the mission, it is only medium risk because the probability of the occurrence is very low. H1, a critical communication failure between our vehicle and the Earth base, is listed as high risk because of its really high probability. Though it may be able to be restored, it's a critical aspect for data communication and collection and must be thoroughly thought out. On behalf of myself, Rachel, Ananya, and Yohannes, I'd like to thank you all for your time. Please reach out for the Mission of Titan group for any questions you may have. Thank you.